Certified separate compilation for concurrent programs. The presentation will be by Anru, and take it away.
Okay, thank you. Good morning. Today I'm going to present how I work towards certified separate compilation for concurrent programs. Compilers are not trustworthy as reported in the previous PLDI work. Even in the most famous or most popular open source or commercial compilers, bug exists. But the author also pointed out that verification of compiler correctness actually helps in improving the situation, that the formally verified ComCert compiler is the only compiler that is free of middle-end bugs. So what do we mean by free of bugs or compiler correctness? Compilation correctness could be defined as semantic preservation, which means the compiled program T has no more observable behavior, such as I/O events. There has plenty of work explored compiler verification since ComCert, but existing work has limited support for separate compilation and concurrency. So why do we care separate compilation? Real-world programs may consist of multiple components. Components will be compiled independently, and program modules may interact with each other. As in this program example, the interaction may include both external function calls and shared memory. So separate compilation, in the situation of separate compilation, the correct compilation means not only the individual modules are compiled correctly, but also the interaction between modules is preserved. Note that here the compiler 1 and compiler 2 can be different compilers, and the modules S1 and S2 can be in different languages. In a concurrent setting, the problem becomes more complicated, where the interaction may include parallel composition. So in this situation, we want to ask, can we reuse existing certified compilers such as ComCert for separate compilation for concurrent programs? There is a previous work of compositional ComCert. They argued that the answer is yes for data-free concurrent programs. The intuition behind this is that data-free programs in interleaving semantics behave the same as in non-preemptive semantics. As in this example, the threads access shared variables within the critical sections, so it contains no race. In this situation, the program is equivalent to a non-preemptive counterpart, where non-preemptive means threads may yield control only at certain program points, like the lock or unlock primitives could be viewed as yield. Note that between the yield points, the code segment is executed sequentially in non-preemptive semantics. So it seems that we are able to use sequential compiler to compile this code. But although the idea seems plausible, we need to address several key challenges to really implement it. The challenge includes these 3 points. The first is how to formulate data-free in a language-independent manner. Recall that the modules may be implemented in different languages. So if we want to give a general semantic framework for supporting cross-language interactions, we need a language-independent formulation of DRF. The next challenge is how to prove data-free preservation compositionally. Although the idea is to require the source program to be data-free, the target program should be maybe the source of the consequential subsequential combination passes. So we require the target program to be data-free as well. But how do we preserve data-free from the source? The third problem is we want to support benign race and relaxed memory models. Real-world library implementation may contain races, and real-world CPUs may implement relaxed memory models instead of sequentially consistent ones. So how do we do these? Our work tried to address those challenges, those challenges. We proposed a language-independent verification framework with key semantic components and proof structures. It supports separate compilation for risk-free concurrent programs with both external function calls and multi-threaded code. Then we extended the framework to support confined benign races in x86 TSO. Applying the framework and its extension, we developed CASComcert, which extends Comcert with concurrency abstraction and separate compilation. We reused a considerable amount of Comcert proofs and also provide a racy x86 TSO implementation of spinlocks as synchronization library. So let me first introduce our language-independent data-free formulation. Recall that data means read-write or write-write conflicts. That means threads cannot simultaneously access the same memory location, and at least one of them is right. We want this formulation to be language independent to support cross-language interactions. Recall that the program modules may be in different languages. And to do this, it commonly means to abstract away language details, such as in the interaction semantics proposed by compositional Comcert. And it specifies only interaction interfaces only, and abstracted away the concrete reads or writes. So the question is, how do we formulate DRF if we do not even know the concrete read or write? Our solution is to give an abstract footprint notion to define data freedom. We define data free in terms of footprint distinctness. Footprint here is defined as pairs of read sets and write sets. To make the abstract notion meaningful while not relying on the concrete language details, we proposed a well-defined language notion as an extensional characterization of footprints. To give a rough idea of what it is, it's actually a set of constraints on state transitions and these corresponding footprints. For example, one of these constraints is that if the two memory states have the same read set, have the same read set, and have arbitrary different contents outside the read sets, executing the same command would result in the same memory effects in the write set. The key idea is that the memory contents outside the read set will not affect the behavior of a command. Putting these a bunch of constraints together, we have the well-defined language notion, which enables us to define DRF as well as footprints in an abstract but meaningful way. Next, I want to introduce our idea about about data freedom preservation and key proof structures in our framework. Recall that in convolutional Comcert's argument, we additionally require that the source program to be data free, and we compile each thread using a sequential compiler. The goal is to prove the above refinement relation between the source and target programs. So the argument said that the compilation should be sound for non-preemptive concurrency, but still we need to bridge the gap between non-preemptive concurrency and interleaving semantics. So our idea is to first introduce these two refinement relations and make the final proof of the above refinement relation turn out as this. The right-hand side refinement is trivial to prove since non-preemptive is a special case of interleaving. But to derive the left-hand side refinement, we need to know that the target program is data free. So how do we know this? Recall that the source program is data free, and the program is actually compiled from the source. We suppose that the compilation preserves data freedom. But how do we preserve this? How do we prove the preservation? Our idea is to provide a footprint preserving simulation. It guarantees the refinement in a non-preemptive setting and also derives the data freedom preservation. In addition, it is compositional with respect to non-preemptive concurrency. Put this together, we have our whole picture of our framework. Here in the box is our compiler correctness criterion. That is, the source and the target program modules should be simulated with respect to, should be related by the simulation relation. That is the footprint preserving simulation. In detail, the simulation relation is a consistency relation between source and target program configurations. It requires that the target program, for each target program step, there should be corresponding zero or multiple source steps such that the resulting states are related by the simulation relation again. So far, this is the same as the standard simulation diagram, but in our approach, we additionally require that the target footprint should be a subset of the source footprint. The key idea behind this is simple. That is, if the target has smaller footprint, then it cannot introduce more races, so the data race freedom is preserved. Finally, we want to give our idea on how to support x86 TSO and confined binary races in our CAS-COM-CERT development. Data race free actually imposes a strong restriction in library implementations. For example, if a multi-threaded client wants to call an external library and make the entire program to be data race free, the library have to use synchronized instructions to access shared shared resources. And this kind of implementation is inefficient. In reality, for example, in Linux, libraries may contain races. It uses instructions that are not synchronized. But it introduces races, and as well, it is actually executed in a relaxed memory model instead of SC memory model. So how do we support these? Our idea is to first focus on confined binary races. We call a data race confined if the race is if the race library and the client code runs in separate memory regions. And also, the client code should be well synchronized, even though the library code can contain race. Finally, it requires that the RACI library have a race-free abstraction, so the RACI program should refine the data race-free counterpart at the right-hand side. Applying this idea, we supported confined binary race and x86 TSO in our CAS-COM-CERT compiler. The source programming language in CAS-COM-CERT is C-Lite programming language. The C-Lite code may be multi-threaded. Thread may synchronize with each other by calling an external race-free lock abstraction. We also require that the whole source program is data race-free. We compile this program in two stages. First, we compile the C-Lite modules using a COM-CERT compiler and get x86 target modules, which is in SC semantics. Then we preserve the lock abstraction, perform identity transformation. After that, we compile the lock abstraction into our manually implemented lock implementation with binary races. And leaves the x86 modules unchanged, but it will run in x86 TSO semantics. We prove that the COM-CERT compiler satisfies our new compiler correctness criterion, and also the spin lock implementation actually implements the abstraction. That is, the implementation and the abstraction satisfies a compositional simulation. In this way, we get the final result that the target program refines its source. More concretely, we redo the proof in our CAS-COM-CERT development of the COM-CERT passes. The COM-CERT compiler contain 20 passes and targeting to 4 different architectures. In our development, we verified 12 of the 20 passes, including all the translation paths from C-Lite to x86. Also, it includes 4 optimization passes. In the development, we reused a considerable amount of constant proofs. For most of the proofs, it cost us only about 100 to 400 lines of code proof. In contrast, the framework itself is challenging to implement. The framework contains more than 60,000 lines of code and cost us about a person-year to really implement it. In conclusion, in this work, we propose a language-independent framework consisting of the key semantic components and verification steps that bridge the gap between compilation for sequential programs and for risk-free concurrent programs. We propose a well-defined language notion for language-independent data risk-free and footprint preserving simulation for DRF preservation. Then we extend the framework. We extended the framework to support confined benign races in x86 TSO. Applying our framework and its extension, we developed CAS-Concert. We reused a considerable amount of concert proofs and provide a RACI lock implementation as a synchronization library. That's it. Thank you.
Time for questions, please.
Leonard Bering, I was one of the developers of the compositional concert.
Yeah.
So I was wondering whether these footprint preserving simulations share similarities with the simulation relations that come from compositional concert, and particularly this footprint and the effects that we were using. The containment relation looks quite similar.
Yeah, actually, our simulation is based on the simulation of the module local simulation of the compositional concert, but we extend the memory effects to footprints. So I think it's a natural extension. And
so that means you extend, in addition to you collect not only the write effects but also the read effects.
Right.
Yeah, the obvious extension. Yeah. Okay.
Yeah.
Maybe related question. So, did you use the structural simulation of compositional concert, or did you use the different technique than compositional concert used for proof of each path?
The proof of each path.
Yeah. So as far as I know, the compositional concert uses structural simulation with the structural injection. So did you use the same technique or?
I have to confess that we have not supported stack pointer escape, so we do not need the structured injections in our proof.
Okay. Because you don't support the stack array.
Yeah, this simplifies the proof a lot.
Okay. Okay. Thank you.
Thank you.
I had a question that may be more speculative. My understanding of concert semantics all the way down through assembly is that it assumes an infinite memory,
right.
Which allows for certain simplifications in the presence of separate compilation, as well as concurrency, because you never need to reuse any memory blocks. You don't have to reason about a memory allocator. Is that just purely future work, or do you think some of the techniques you developed here would support a finite memory by simply thinking of the memory allocator, the runtime memory management, as a separate composable feature, perhaps?
Currently, we have not considered finite memory yet, but we believe it will be able to extend our framework to support this. I think there was work on stack-aware concerts that have done this thing before. So it's natural to consider how to extend their work for concurrency.
Do you think there are challenges between? I mean, there's a big difference between finite stack and finite heap, perhaps, or do you think maybe it's not that big of a difference?
Actually, I do not expect particular technical challenges with concurrency present.
All right, let's thank our speaker.
Thank you.